Today, we're going to be going over CO2 safety and handling. One thing that Louis and I both noticed throughout the industry is there is a lot of training on the books and the very technical end of things. And what we noticed is it's been a little bit takeaway from the technicians, and that's what Louis and I kind of want to get back to is bringing that technician level back to it. So, my name, we'll get right into it. And my name is Adam Rumps. I'm one of the field training managers at Climate Pros. I've been with Climate Pros for about 7 years now, and I've been in the industry for overall 13 years. So I specialize in supermarket refrigeration. I've always enjoyed making things cold. So I'm going to pass it over here to Louis. Oh, Louis, you might be muted.
My apologies. Can you hear me now?
Yep.
All right. Thank you for that introduction, Adam. Thank you, Morgan. Excited to be here today. My name is Louis Smith, one of the senior technical training managers at Climate Pros. Similar to Adam, I've been in the trade 13 years, been at Climate Pros for 11 of those years. I've held various positions throughout, starting as an entry-level technician up to the technical training manager at this point. And Climate Pros invested heavily in their technical training. I'm just excited to be a part of that and excited to be able to bring that knowledge to you guys. So I also specialize in supermarket refrigeration.
Yeah, so some of the things that we're going to cover today are identifying conditions of trapped liquid and hydrostatic pressure. We're going to review safety scenarios, how they occur, and how to prevent them when dealing with CO2. We're going to go over some technician hazards and preventative measures, and go over some concerns at the store level. So I know we might have some of you individuals here that are store managers or designing stores, and we want to go over some of those store level concerns as well. So our goal at Climate Pros and with this webinar is to help you be more efficient, comfortable, and safe while working with CO2, because working with CO2 should never feel like defusing a bomb. All right.
Yeah, sometimes it does, right, Adam? Guys get timid, they get a little scared, the pressures are high. All we're trying to do is keep the product cold and our bodies warm, right? So
Yep, for sure.
it's not rocket science out there to try to debunk some of those myths that a lot of guys are concerned about. So
Definitely.
kicking it off, a lot of you might know this already. Again, these are some of those things that are often talked about when we talk about CO2. Um, we do feel it's important that we talk about it a little briefly, acknowledge it, so that as we get further along in this webinar, things make sense. So one thing to call out that's always called out, I feel like, is the critical point. All right, 87.8 degrees or 1055 psig. All that's saying is that once you exceed that point, refrigerant becomes a supercritical fluid, only able to remove that sensible heat from it. We're not changing state anymore, so things get a little bit haywire. It's not something that didn't exist in the past. It's just something we never dealt with in the past because it's never been this low. So that's one of the newer things that you're going to hear a lot about when you're dealing with CO2, and then a lot of people have talked about in the past. The next thing is the triple point. All right, the triple point for all three phases meeting equilibrium, they all coexist, and that's where you get that dry ice at 60 psig roughly. Um, Once you introduce liquid before that, that's when dry ice occurs, and we're going to have a lot of scenarios where we're going to talk about that coming up here. Next, naturally found in the environment, another big one, although maybe the CO2 we're using isn't necessarily naturally found in the environment, it's harvested or a byproduct of something else. It's non-toxic, doesn't harm the ozone, and it's colorless and odorless.
Hey guys, so now we're going to get into our safety concerns and what those safety concerns are throughout our working on CO2. So our first safety concern that we're going to talk about is trapped liquid. This is a big concern for most of our technicians out there, also called hydrostatic pressure. So what is hydrostatic pressure and how does it occur for CO2 systems? Hydrostatic pressure is liquid CO2 becoming trapped in an enclosed section. So it could be our piping or a component that needs to be changed out. Uh, it, that liquid CO2 becomes trapped, doesn't have anywhere to escape to, and therefore and uh, expands at a rapid rate. So one thing to note with liquid CO2, for every 1 degree Fahrenheit increase in temperature of that liquid, it'll increase 80 psi. So it's very fast and it can happen very rapid, right? So this is definitely something that we want to pay attention to when we're isolating components. Luckily enough, for our manufacturers thought of this ahead of time, and they installed some safety precautions on our systems to help mitigate this risk. So the first one that we're going to talk about here is that internal pressure relief. So these are our ball valves with that an internal check that allow that pressure that might build up on the evaporator coil if we're doing any sort of work on that evaporator coil. Maybe we're changing that basket strainer out on that pulse valve and we have to isolate. If that pressure builds up, it'll push back on that internal relief and blow back towards the vessel. It's not going to be an external relief. It'll actually stay within the line and blow back towards that vessel. All right, back towards the rack. Louis, you want to go over the other scenario we got here?
Yeah, so the next one we have is the external check valve, one that we've seen in the industry for years. Um, and it's just simply a bypass around the check valve. All right, if you see that, those are things that you're looking for when you're isolating components. Is when you if you're going to shut off ball valves and isolate refrigerant or trap refrigerant between 2 points, how can this refrigerant escape before you have time to service it? Right, those are things you want to be thinking about. Or if you're going to be doing a job, and we're going to talk about that later. If you're doing it, if you're working on a specific job and you're going to isolate something, looking for how that refrigerant can escape and being prepared ahead of time to get that job done within a reasonable time. So we'll talk about that in a little bit here. The next mitigation effort we have is, so we got two, relief valves or check valves, bypass valves. The next thing is ball valves specifically used for CO2. And one of the primary differences is pressure. That's a big one, right? These ball valves are rated for a higher pressure. So if they're on the high side of the system, but another big important factor to these valves is they have a little eighth-inch drill hole in the actual ball valve internally. And what that does is when you turn the ball valve, you're not trapping that refrigerant inside the valve. It allows the refrigerant to escape. So we have a little animation on what that looks like. As refrigerant's coming through and we close down this ball valve, and this would be that little the silver ball, stainless steel ball inside the valve, it closes. You have the potential to trap liquid here. All right, so pressure builds up. And if you didn't have this little porthole for that refrigerant to escape, that's when it can explode. So that's things we need to be aware of when you're replacing ball valves as well on a CO2 system. It's not just grab one off your truck. All right, having the right parts available.
Do you imagine the first guy that put this in and realized, oh crap, I'm trapping that liquid in there?
Somebody learned the hard way, right?
Yep, for sure. So here we have an example uh, of an occurrence where we didn't have these safety precautions in place. So what happened here is this was actually a coil that was in the back warehouse for heat reclaim. And what happened is it didn't have any of those reliefs. That didn't have that check valve bypass or that internal bypass or even just an external relief to blow off into the area. And what happened is the CO2 got trapped in that coil. It started to heat up and expand rapidly to the point where it blew apart this manifold on this coil. It actually put a hole in the wall in the back warehouse, quite the mess. But it's definitely a concern. And this is something that we need to think about when we're doing new installs is double checking our system as a technician or even construction crew going through and putting these in, making sure that we have those bypasses in place so that we mitigate this occurring, right? So always stay conscious of that.
Hey, good stuff. Adam, really quick, we got our first question. Is it advisable to use both systems, the bypass and the check? They're interchangeable and they accomplish the same thing, right? It's just two different components. I believe it's Sporland built a valve where you can essentially install this valve instead of doing the bypass as well. So good question.
So, and you can see in that other photo on the right-hand side there, we have both examples. They might not be on the same pipe, but we have the ball valve with that internal check and we have these bypasses. So it could just depend on the cost too of the install, what's more preferred. But they should be there. You always want to have a spot for that CO2 to escape.
Thank you. We hope we answered that for you.
Yeah, so here we have another example of trapped liquid. And in this scenario, what happened was was a new construction site and a new install. What happened was the evaporator piped configured different than what was spec'd for the store. So it was actually piped set up for a hot gas defrost. And we found out that we're not supposed to be piping it that way. So in order to to fix that, it was instructed to cut out that hot gas. And with that being said, it was cut after the check valve there. And what happened was that check valve, you can notice those dimples on that check valve. It released back into where that braze joint is. So that's where that gas is going to flow through. Now, because it is a check valve, that gas isn't going to go back across that check valve. And then we have a braze joint there that's just blocking the flow completely. So that liquid built up enough pressure, and that CO2 gas built up enough pressure to blow apart that braze joint and release the charge. And unfortunately, they lost the whole charge of refrigerant on this rack because of this. So in hindsight, we should have went back behind, or the individual should have went back behind the check valve and cut it there and made sure that we had some sort of bypass in place for our evaporator. So just another example for you guys to see and to be cautious of when you guys are doing any sort of repairs or any other installs.
Yeah, so this isn't just fear mongering on the high pressures, right? This is just awareness, things we need to be aware of, things we need to be looking at. And in these both these scenarios, it came from the install, right? The original install. So this would have happened early on. So things to look out for if you know that a store is newer.
All right, so our next safety concern is dry ice. Dry ice can cause frostbite. You can get burns from dry ice. Not only will we potentially come across dry ice physically right in front of us, but you might find dry ice within the system. And the reason why dry ice occurs with CO2 is because liquid CO2 gets introduced into an area that is below that triple point that Louis mentioned at the start of this, right? That's 60.4 psi. Once liquid's introduced any pressure below that, it can instantly turn into dry ice. So we need to be cautious of this. Where we typically see this most common for service technicians is when we're doing our filter core changeout, right? So that's a liquid filter core, liquid filter dryers that take routine maintenance where we're going through and having to change those out to make sure that we're cleaning up the system. Um, so in this instance, you might find dry ice within that vessel, that shelf that holds those filter cores, right? So it's not recommended that you just go reach in with your bare hand, scoop out the dry ice. Dry ice can cause severe frostbite and burns to your hand just right upon contact. You don't have very long. So it is recommended you have proper PPE. Whenever you're dealing with a vessel like this too, you should not be going and looking straight down that vessel. All right. You want to use a mirror and you want to reach from the side to remove any dry ice. Use a brush of some sort, but we shouldn't be looking down these. Just like what we do when we go and turn on our electrical breakers, we step off to the side and turn it on. The same thing goes with these vessels here. I've had buddies actually in the past that working on traditional HFC systems, they were changing a liquid dryer, and unfortunately, a ball valve failed while he was cleaning the screen on the actual dryer, and lost that whole charge. But if he was looking down that vessel when that ball valve failed, that could have caused serious injuries, and we don't want to run that risk, right? Use a mirror, look down it, see if there's any debris in there.
Good stuff. The next one. So in this scenario, this is a real image pulled from a video. We photoshopped it, blurred out as much as we can to protect the customer, the company, and the individual. But we feel it's very important to talk about because Adam and I spent a lot of time talking about safety and doing things as safe as possible and taking the time to do things safe because it does take a little bit more time sometimes. In this scenario, there's just a couple things to call out. This individual was blasted in the face with CO2. That's liquid CO2 hitting them. So there's a lot of hazards all in one photo here. And throughout in the video, when you watch it happen, the individual, one of the first mistakes that happens is he opens the tank right in front of him. The tank is facing his chest as he opened the tank with a brass fitting on there that ultimately ended up becoming a projectile. All right, but he stood in front of a tank and opened it. A safe method of doing that is standing to the side. All right, stand to the side of the tank, point the tank away from you, and open it. Technicians make this mistake all the time when you're dealing with oxyacetylene. You're on you squat down, turn on your oxyacetylene, and you're standing right in front of your regulators. Those regulators fail, or you have those regulators cranked all the way in on a new tank. Something dangerous can happen. Those things can shoot off. So that was one of the early, first mistakes. The second one is something I'm gonna let Adam elaborate on a little bit because it goes back to understanding the triple point and proper charging and purging practices. You want to elaborate on that, Adam?
Yeah, so whenever we're charging our systems and we're using these CO2 cylinders, we always want to make sure that we're going from the system vessel back and purging it back to the tank. Okay, so in this instance, what we speculate occurred here, and we can kind of tell by nothing coming out of that soft copper, is that when the tank was opened, we didn't have any pressure build up in that line set, right? So therefore, once that was open, we had liquid CO2 entering into essentially atmospheric pressure. So with that formed dry ice around the nozzle of that tank, right? So and that's because it was below that triple point, like Louis mentioned, it was below that 60.4. So we want always make sure that we're purging and pressurizing that line back from the system to the tank. And in this instance, that dry ice beat it up to the point where it almost seemed like time stood still in the live video. Once it was uh, opened and moved over, noticed that there wasn't any flow, looked at the tank, and now he's getting that CO2 to the chest there, that liquid CO2, which can cause some significant injuries, right? Worry about burns, um, frostbite just from getting hit from that liquid CO2. So another thing too, guys, always wear proper PPE. Make sure you have gloves, glasses, help protect your eyes. Hopefully this doesn't, after this webinar, hopefully you guys don't come across a scenario like this, but it is a
Unfor-
learning experience for everybody.
Yeah, unfortunately, it's out there. It's common. A lot of people are using soft copper to charge CO2. That tank at 75 degrees is just under 900 psi. That's already over the rating of the copper. So without that system being opened up to the actual rack, you're introducing 900 psi again just at 75 degrees to that line, which exceeds the rating of the copper and very likely the fitting that was on there too, the flared fitting that he had to go to the CGA fitting. So just things we need to be aware of and tackle the appropriate way in the field. We're going to talk about how to do that here in a minute.
And just like what Louis mentioned, whenever we're working with CO2 and charging CO2, we never want to charge with soft copper. There are proper tools that we should be using in order to charge our system. I understand there might not, sometimes it might not be an option, but maybe we can have that discussion with the customer prior to, or even your service manager to make sure that we are staying safe, because it's ultimately up to you to make sure that you're getting home each and every night. So do not use soft copper. It is not rated for the pressures of CO2.
Good stuff. The next thing, all right, this is where I can get on a soapbox a little bit because I hear a lot of discussion in the field back and forth on if technicians need gauges out there, and the overwhelming majority I hear no, and that it it grinds my gears. To me, that'd be like walking into a doctor's office. You know, you're not feeling well. You go to a doctor's office and they say, "Hey, let me see your Apple Watch so I can check your heartbeat." Right? You'd be a little hesitant. I'd be like, "What? Where's your stethoscope, dude?" Like we should be walking into service calls just like they walk in their office with a little stethoscope around their neck, right? Have some gauges, have the right tools to do the job. And the biggest argument we hear against needing a set of gauges or needing a gauge is that there's gauges on the system. All right. There's already analog gauges built on these systems. These systems are sweet. Well, that we're still in the early stages of that, right? We're just a few years into seeing that. Get 10 years down the road, how do you think what kind of condition do you think those gauges are going to be in? Adam's got a little story on that one.
Right. Yeah. We actually went out into the field just recently, a couple weeks ago, and we are pumping down a vessel to do some work on a liquid level changeout, liquid level sensor changeout. And we noticed our gauges, we brought gauges with us and hooked it up right where the analog gauges were for that came with the rack, and noticed that there was about 150 psi difference between our gauges, what the system was reading, and then what those gauges that actually came on the rack were reading at. And 150 psi could be the difference between a system popping off or not, right? So having your own set to make sure you're taking the correct ratings or readings uh, is crucial.
Definitely. So we're not advocating you go run out and buy a set of gauges, but a gauge, right? A lot of our technicians are using the little stubbies in the field. If you don't necessarily need a manifold set, you need something to be able to check system pressure, right? We're not just putting our ear up to it or relying on the existing tools on it. So as a technician, yeah, we firmly believe you should have the right tools for the job. And the one we got here on the left is just a long set of gauge made out of a Kevlar material. That's available for purchase where you can, and these are great. They come in, you can get them any length you want, 5 foot, 10 foot, 25, 50. Those are going to be critical when you're doing those dryer change outs or you're trying to reduce pressure from one section of the system to another. Having just the right tools to do the job, or when you saw that little soft copper connection up at the roof, having the right, there's a hose that's supposed to be used for that, right? And there's hoses rated for CO, the pressures of CO2. That soft copper is not it. All right, they do exist.
Yeah, sometimes it can be hard to find. It's becoming more prevalent now that we're seeing more and more CO2 systems out there. Um, but for a while there, it was a little bit tough to find specialized tools for CO2. And we noticed hydraulic hoses. They can handle the rating. You might need to get some fittings that also make sure that they're rated for the CO2. But yeah, you can utilize those hydraulic
That's where
hoses.
a lot of our guys went. They went
Yeah.
to hydraulic shops, because unfortunately, you walk into one of our suppliers or regular suppliers these days, and they're still not fully equipped to handle CO2. So we got to be a little more creative there, but it does exist, guys.
And again, going back to the hoses and proper charging practices, uh, one thing that we noticed going out in the field and what guys were sending us pictures back of is a lot of guys were kind of makeshifting their own charging station or their own charging hoses, their own charging setup, and they're taking just general brass fittings, uh, general brass ball valves, and then even tossing a sight glass in between the hose and their brass fittings. And we do not recommend that. And the reason for that is because those sight glasses are not rated for CO2. And if you're an individual that's on site trying to charge a system by yourself, we don't always have charging stations in the store that drop down below. We might have to run a hose from the side of the building down. And then with that, though, we should be contacting the customer, letting them know, hey, we might need to get a charging station in here pretty soon. But sometimes you might have to run that long hose. And if you're an individual that's trying to charge a system by themselves and you have purged it and you're sitting there having to go back down to the van to open up that CO2 cylinder, now that pressure is building up on your hose, building up on that sight glass, and it's a risk for a potential rupture point. So
There's been guys out there doing this for years, like, and there's arguments that can be made. Hey, I've been doing this for years and it works just fine. And you might hear that, and it's all good and dandy until it's not, right?
yeah,
Until something bad happens. With proper practices, technically as long as that hose is open to the system at all times, you're not going to see that 900 psi on that hose. But to Adam's point, if you're a single man out there charging, trying to, dropping stuff off the side of a building, trying to put gas into a store, that's when bad things can happen quick. I've personally called the different manufacturers of the sight glasses to ask them what the ratings are, and they all average between 6 to 800. And then and then back on the manifolds, why isn't there a sight glass charging or a sight glass on the middle of the CO2 manifold? It's because it'd have to be super thick in order to put one on there. It's not worth it to them. So there's a
yeah.
reason they're not there.
And in the photo on the right hand side there, this is a picture of a charging setup that was designed for CO2. This is actually a pretty cool setup from one of the guys in Florida. He was able to pick it up at one of the conferences down there. But this is actually a CO2 regulator for charging. So that handle there on the left-hand side allows you to set your pressure to allow a certain amount of pressure to come through. And that's why with this system, we can have that sight glass on there because one, can regulate the pressure coming through there. And two, there's also an internal relief port. So if any pressure does build up, it's going to relieve through that pressure relief there. The other cool thing too is that it has that ball valve made for purging. So it makes it a lot easier for purging your system.
Yeah, it's a pretty sweet setup. I hope it becomes more readily available. At this time, I don't believe it is, but one of our technicians got a pretty sweet deal on it. He's able to take that 900 pound tank down to 600-700 pounds just over the flash tank, so he can charge the system safely. So
All right, our next safety concern that you guys might come across, not only for service technicians, but even for employees of a store, is suffocation. One of the things that we have to worry about with CO2, like Louis mentioned earlier, it's not, it, it doesn't have an odor to it like we do with like propane or natural gases. We don't add any scent to our CO2, and then also you can't taste it, you can't see it. It doesn't exactly make a cloud when it's coming out of the system. You might see a cloud, but when it's just barely leaking through, you're not going to be able to see it. So this is a concern. And actually, I have a story from when I was an apprentice going through. We had a restaurant actually call in indicating on a Monday, of course, that their walk-in happened to just go down that morning. We found out after going in and looking at it, we found about 4 inches of ice sticking off the backside of the evaporator. So it didn't happen that morning. But me and the journeyman went in, started de-icing that coil, and as we were doing that, me being an apprentice, I was nervous to say anything to him. Uh, I started to having issues breathing, and luckily the journeyman turned to me and asked me, "Hey, how are you feeling? You feel lightheaded at all?" And I told him I was like, "Yeah, man, I feel a little bit strange." And he indicated, "All right, let's get out of the walk-in." We went over and talked to the restaurant manager, and come to find out on Friday when the system was really running warm, they went out and they were buying large amounts of dry ice so that they could put it and try and save the product. They'd put it all throughout the walk-in. And by the time we got there, all of that dry ice sublimated off. And that sublimation is just going from a solid straight to a vapor. So there's no transition from solid to liquid. It's just straight to a vapor. So there's no puddles or anything showing that. But that CO2 will cause that lightheadedness, that dizziness aspect. So for our refrigeration grocery stores, what this means is if we're working inside a walk-in or a POS freezer, POS cooler, or any confined area with CO2 system, we want to be mindful of how we are feeling. If we're having those issues breathing, if we're getting dizzy, you need to exit that area and you need to talk to the store manager and let them know we need to ventilate this area and we need to make sure that no one else is going into that area. Because the last thing you want is for someone to go and spend time in one of those walk-ins and for them to pass out. So it needs to be blocked off, ventilated, and before we start trying to attempt to fix that leak.
yeah, too much of anything is not a good thing, right, Adam? So
Right,
pretty
for
much goes
sure.
for anything there.
Yeah.
So good stuff. All right, our next safety concern, we got high system operating pressures. This is the big one, right? This is the one that when CO2 came out, uh, people are pretty concerned about it. Still tend to be. We talk to a lot of technicians daily, and it's still always a concern. When you it almost goes back to it turns a journeyman into apprentice again. Like, hey, did you go check the system pressure? Well, yeah. I mean, it says this on the E2. It's like, no, go get a gauge, put it on there. Go look at the one already built on the system, right? No. Um, so talking a little bit about pressures, we want to go through some of them. Your low temp suction, you're running 200. Medium temp suction, about 400. Flash tank pressure, it's right around 500. All right. If you've done any commercial HVAC in the past, in the last 10, 15 years, you've been dealing with 410A. These are very similar pressures to what we were already dealing with and already seeing. It's not until you get to the discharge side, the high side of your system, where you're seeing that 750 to 1300, 1400. All right. So overall, the majority of the system that we're working on in your evaporators, out on at the flash tank, it's the lower side of the system, the suction. It's the pressures aren't too bad and similar to what we've done in the past. So we have a little animation or diagram that I think helps break that down and try to take some of that concern off and just awareness for the technicians. Highlighted in red here, that's where you're going to see that 750 to 1300, and that seems to be the only part. When you hear about the high system pressures, that's all. That's where it all comes from. Is this little part of the section, the little part of the system right here, and the rest of it, you're operating about 500 and below. Right? It's not that bad. Adam, in that stuff in the red there, what does that tend to be?
Yeah, it's gonna be up on the roof or out in the rack house. It's gonna be outside. Allows
Yeah,
for hopefully an easy exit if
fairly small
everything goes
portion of what
well.
we're doing,
Yeah.
but just bringing awareness to that. Not saying we shouldn't respect it, but you know, it's also not quite as bad as I think a lot of people think. So when you break it down like this,
Yeah, so Louis, that being said, if I'm charging a system and let's say I don't have a charging station inside the store, if I just think if I can easily get to an evaporator coil, is it a good idea to take those tanks in there and just charge right at a case, glass doors?
so I've heard a lot of discussion on this one, and this one's, it's been told that it'll void your manufacturer warranty, and the reason is because cases, everything in blue here is typically sized at 45 bar or below. It's something that NASRC I know is actively working to, and having discussions about to try to increase that, because right now we're looking at about 750 pounds, and like we said earlier, that tank is sitting at 900 pounds, 900 psi. So that pressure being introduced into an evaporator could damage that coil and create leaks prematurely. So it's not advised. Ideally, we want to go up into the flash tank. So if it's and that's something we'll get into when we talk about from the customer perspective how they can help with that. So
Right on.
next, we want to take a pause, do a quick recap on where we're at in this presentation and what we got coming. So a little recap, we talked a lot about safety, talked about hydrostatic pressure, suffocation, dry ice, high system pressures, a lot of the concerns that are commonly brought up when you're dealing with CO2. We talked about equipment, having the proper tools for the job, things that we should be prepared for, how we can be better prepared to do the work. The next part of the presentation, I'm going to turn it over to Adam here. This is where I think things get a little bit fun. All right, we're going to try to teach you how to tackle different scenarios.
Yeah, so we're gonna get into a tech talk where we're talking about different service scenarios, going through common practice, some of the common scenarios that we see mo most of the time. Uh, and then we're also going to be getting into customer awareness and some of the considerations on the store level and what can help mitigate some downtime. So our first scenario that we have here, very common one that most technicians deal with on a weekly basis, is having an iced up coil. All right. So with CO2, surprisingly enough, guys, it's not much different than our traditional HFC systems. All right. We're going to start by shutting off our liquid line ball valve. We'll shut that down, stopping that flow of that liquid CO2 to our evaporator coil. And then we're just going to go through and start de-icing. Now, with CO2 systems, where it's a little bit different on here is you might see a suction ball valve within that case. Okay. But just because it's there doesn't mean you need to shut it off. All right. You're going to do it just like you would in traditional HFC. Shut the liquid line off, leave the suction ball valve open. That way, as you're adding and spraying that hot water across that coil, getting rid of that ice, any pressure that builds up is just going to flow right through your suction line because the rest of your system's operating. It's running. You have other compressors that are running, right? So you don't have to worry about that pressure buildup.
This is one Adam and I get all the time is we said we hear from journeymen too, like is it safe to spray hot water on this coil? What's going to happen? It's like, well, as long as you're not shutting off that suction and the gas has somewhere to go, you're going to be just fine. Technicians have been doing this even in the States for over 10 years. All right, so you're not going to have an issue there. But again, it just comes back to just dealing with the loop system and seeing that ball valve, and we just want to close it off. We want to touch it. You don't have to. All right, so leave it alone. Close down your liquid, de-ice the coil, and you'll be just fine. What
The
you
other
are
thing,
doing is go on, Adam.
yeah, the other thing too, guys, is you shouldn't be relying on those check valves. So those check valves are the bypasses around those ball valves. Um, some guys have argued in the past, well, I shut them both off. I have those check valves where it'll release back. But we shouldn't be relying on that, right? That's a mechanical component that we're then putting our safety in the hands of that check valve, right? If I can just leave a ball valve open and allow that pressure to flow through, might as well, right? So helping to understand that flow of refrigerant and where it's going to go. All right. So our next scenario here is circuit isolation. So in this scenario, let's say we have a pulse valve screen that we need to change out, the basket strainer in that pulse valve. So now this is a little bit different than that de-icing scenario that we gave, right? But surprisingly enough, it's not much different than what we would do with an HFC rack. All right, changing a screen on a metering device. In this, we have a pulse valve. We're going to change out that basket strainer. We're going to start out by shutting off that liquid line ball valve, and we're going to use our stubby gauge and hook up on our suction line and watch our pressure pump out through our suction. So we're just going to let this system pump out and come down to suction pressure. Once we come down to suction pressure, we can then shut off that suction ball valve here and watch our pressure. If our pressure starts to increase on our gauge, that's an indication that you might still have liquid on there on the coil, right? So as once you indicate that you might have liquid on there, if you can try and get that CO2 over into the system, if this is a medium temp case, you would have to take it to a low temp case. That's not always the scenario though. You might not have enough hose to reach that. Um, but what you would do is either open up that suction ball valve again, let it pull back down to suction pressure, close it off, watch your gauges. Is that needle going back up? Do I still have liquid boiling off? If that's the case, do that again, and then we get to where that gauge sits stagnant, and you leave that suction ball valve closed. Now you still have pressure on there, right? So the one thing that I want you guys to pay attention to is with CO2, the nice thing is we can vent off because we don't have any sort of reclaim machine that can handle those pressures, and it is naturally occurring. So we can vent to the atmosphere. But if you're in the middle of an aisle, the ice cream aisle, and you have shoppers all around you, do you think it's a good idea to just open up your hose and just let it go in that aisle? Like you're putting on a AC/DC concert coming in, get the fog rolling through the aisle. No, that's not a good scenario for those customers. Um, Again, CO2 displaces oxygen, right? So we want to do a nice controlled release, do it slowly, make sure we're in a ventilated area, and then get that coil down to zero. So now with it at zero, go through, clean out that basket strainer just like we would with a traditional HFC system, put it back together, and then we're going to pull a vacuum. Always pull a vacuum when we open up a system to the atmosphere. All right. CO2, we still want to make sure we're pulling non-condensables out. We want to get moisture, any moisture buildup out of the system, we have to pull a vacuum. So once you pull that vacuum and you're ready to start the system back up, this is where it gets a little bit different than our traditional HFC systems. And that being said, what you'll start first with is opening up your suction ball valve. The reason we're going to open up that suction ball valve first is because we know on our suction line, we have vapor CO2. All right. Remember, if we introduce liquid CO2 to anything below 60.4 psig, that can cause dry ice to form. So we want to introduce that vapor CO2 to the coil first to help build up that pressure. And like Louis mentioned earlier, our low temp suction is going to be at about 200 psi. That's well above that 60.4. So we know we're not going to build up any dry ice inside there, and we'll build up enough pressure. So then once you get that pressure on that coil, you can now go back and open up your liquid side ball valve after you go through and leak check all your work.
Good stuff. Thank you, Adam. Next one, we got component isolation, talking about a oil separator filter. This one is coming up multiple times as well, not just for service, but for routine PMs as well. We've had requests often to go out on site and assist with this task because it seems daunting. But again, we trying to keep things as simple as possible, very similar to just dealing with HFC systems. The shutdown of the rack is going to be very similar. Close down the outlet to the flash tank, let it pump down a little bit, turn off and kill your compressors. Now that the rack's dead, we're ready to change out the separator filter. We're gonna go. Normally, there's not a ball valve before the separator. Unfortunately, we always wish there was. Never seems to be. Right. So you go to your discharge valves on your compressors. Turn all those down. Now the inlet to your separator is isolated. The critical step next is going to the outlet and looking at the outlet of the separator. there's usually a check valve there. And I've seen too many technicians and heard of too many technicians who will rely on that check valve as a shutoff or isolation. It is not, and it should not be treated like that. You go move downstream, find the next ball valve, either before the heat exchanger or before the condenser. All right, find the next set of ball valves. What that means is you're gonna have to blow out some more refrigerant. You're gonna have to pull a vacuum on, I like to go on both sides of that check. Um, but it's worth it, right? It's doing things safe. The last thing you want to be doing is having the top of this separator open, reaching your hand down, and then that check valve lets loose. All right, so isolate properly. Obviously, we're going to close out the oil inlet on the bottom, and once that separator is isolated, we're already a vapor, so we don't have to worry about, you're not worried about creating dry ice or having any immediate issues. Once you're a vapor, you can let it go to atmosphere, blow it down. We don't have to pull our reclaim machine up there anymore and move it over, to the suction. So let it rip, set and change out your filter, pull a vacuum, and we can just now we can open our ball valves again. Because we're on the high side. It's a discharge. It's a discharge vapor. So we're not worried. We don't have to worry about going backwards with the suction. It's already in the gas state. We're not going to create dry ice. Open it back up, and you're good to go. Always leak check your work, right?
Yeah, and Louis brought up a really good point there too about looking at the ball valves down the line. For any service work that we're doing on any system, we should be looking at where our next shutoff valve is, right? As we stage up the job, take a look at your lines that you're isolating. Make sure you have a spot for that CO2 to move back through. Make sure you know where your next shut off is, right? Um, and this is one thing that Louis and I do to this day is anytime we come across a new system, we go through and we literally trace out the lines and we will physically touch it and walk through the system so that we know what the flow of refrigerant is and understanding where that refrigerant's going to go. So not just with CO2, in HFCs as well, making sure
Yeah.
you know that flow.
No matter what level of experience you are. It's always, getting to know the system, a new system that you're gonna be working on is key, right? Especially in the event that something bad happens. Understanding, yeah, I love that theory, knowing where your next shut off is. So the next thing, adding oil. This is something I do the second I arrive on every service call, right? So I'm just kidding. I'm just kidding. All right, but adding oil is a thing. We've gotten questions about adding oil. Hopefully, at that point, if you're going to do it, you found a huge puddle somewhere, or the technician's covered in it. All right, they're ready to add oil to a system. The question becomes, how do we do it? The pumps that technicians often carry on their trucks are only rated to handle 200 to 250 psig. Trying to pump into a 500-pound to 1,000-pound oil reservoir is not going to go well. All right, so the easiest way to do it is isolate the inlet, isolate the outlet. If you got an equalizer line going back to the flash tank, isolate it. This is where it's nice to have a set of gauges or something to read pressure, because now what you could do is start to throttle that pressure down. Let's say it's at 500 psi, bring it down to 100 psi. Watch it on your gauge. Get on the bottom of it and start adding oil into the bottom of the reservoir. All right, same process as adding oil to an HFC rack. The only difference is, again, the isolation and bleeding down the pressure. So it's something that's manageable. All right.
All right, our next service scenario here. The example that I'm going to use here is you get a call for a power outage out at a store. And as technician, sometimes we might arrive on site before that power comes back on. So one of the first things that you want to do is go through and shut off all your disconnects to your components and your circuits. So shutting off your disconnects for your compressors. All right. That way, once power does come on, it's not all at once, right? So systems are traditionally set up now to where they mitigate that, but just as a precaution, we should be powering that stuff down, shutting those disconnects off. So once that's done, now the power's back on the system. One of the things that we're going to want to check as technicians is see if we have any liquid inside our compressors. If you live in any of the colder climate area, such as Midwest, UP of Michigan, any colder sort of climate, CO2 still likes to migrate to the coldest spot, just like our HFC refrigerants. So that might be your compressors in this scenario, right? So we want to always check and make sure that we don't have liquid in our compressors because we can't compress a liquid, right? So another thing to note too, if you do find liquid inside your compressors, a there's a good possibility that that you're going to have liquid inside your suction header. So in that instance, you're going to have to isolate each individual compressor. And the nice thing again with CO2, if we can't move it from one spot of the system to the other, and we can, what we can do is vent it, right? So you might have to vent off that compressor to try and get that liquid CO2 out of there. So now let's say that scenario, you don't have any liquid in there and we're ready to start back up. What we're going to do is we're going to start with our medium temp compressors, our first and smallest compressor on our medium temp side. We always start up our medium temp before our low temp, because if you notice, our discharge from our low temp compressors goes directly into our medium temp suction. So if we started the low temp, we could cause some potential issues on those compressors, cause internal damages, go off on safeties. So we always want to make sure we're starting up our medium temp first. And we're going to stage it. We're going to go up, bring it up slowly. All right. So start with one compressor, bring on a few circuits, move on to the next compressor, bring on additional medium temp circuits. And you want to do that uh, in a slow pace and make sure that your medium temp starts to get close to that set point before we bring on our low temp
That's
compressor.
critical too. That's where a lot of guys make mistakes. Is you got a rack down scenario, and the technician's in a rush trying to get the rack back up and going. You got the pressure. Product's warming up. Store manager might be breathing down your neck. And your goal is to get that thing going. And the natural reaction is let's get this rack running. So guys will just start turning on compressors and trying to get it going, and it trips on high head again. Trips on high head again. It's because you're bringing so much load back, so much system heat back into these medium temp compressors, and you can't discharge it quick enough. All right, so Adam and I like to teach slow, smooth, smooth is fast. All right, get that medium temp going. Let the suction pressure stabilize. Let some of those medium temp circuits start to come down to temp before we start to go fire up our first low temp compressor. All right, slowing down that process just a little bit, to give the system enough time to keep up, will go a long way. All right.
And that is something too that I've come across in the past where guys are concerned about getting their low temp stuff up and going so that they don't have ice cream running out the glass doors in the aisle, and they just jet straight to the low temp side of the system and start turning those compressors on. Our system can't run with just the low temp. Our medium temp has to be running first before we bring on our low temp system. So keep that in mind. Yeah, like Louis said, slow is, or just go
Slow
ahead,
is smooth,
Louis.
smooth is fast.
There you go.
So, all right.
All right, so now we're going to get into our store level considerations, things for you guys that have employees that are working on the store level or are going and transitioning from HFC systems to CO2 refrigeration systems. So one thing to be cautious of, just like what we talked about earlier, nauseous or dizziness. If any employees are coming to the manager, the store manager coming to you indicating that they're getting dizzy, they're getting nauseous, that could be an indication that you might have a CO2 leak on your refrigeration system. So we need to take those seriously and give a call out to our contractor so we can get out there and leak check and make sure that we're not losing that charge. Therefore, you mitigate downtime on your product and make sure that your employees are staying safe as they work inside that store. All right. The other thing too is what we've noticed is a lot of customers are storing their own CO2 tanks on site, just in case they do have a situation where they need to add refrigerant or there was a leak. So one thing you want to be cautious of when you're storing these, you want to make sure that they're clear of any pathways and that they're roped off and tied off uh, out of out of any of the high traffic areas. The other thing too is to keep these out of direct sunlight. We have seen an increase of some customers storing them outside, but with that, we want to make sure that they're under some sort of cover so that the sun isn't just beating down on them. So that the pressure in that tank, just at 75 degrees, is just under 900 psi. So any additional heat added to that, that just means that pressure is increasing on that tank.
Yeah. Next thing we got is sizing for redundancy. If you get ahead of the game and you're putting in a CO2 system, some of the common components that tend to have the longer lead times or cause more downtime are your high pressure valve, your flash gas bypass valve, maybe the controller for that. When you have critical components within the system that can lead to long downtimes, those are things that size for redundancy. Pipe those major components in parallel. Oftentimes your bigger applications will do that. Supermarkets, in an effort to save costs and I believe space as well, it's not often done, and I think it should be more common practice. I think it'll lead to more customer satisfaction and less downtime for the customer as well. And if you already got these systems in your store, just having these working with your contractor, find out which components can lead to me having severe downtimes, or historically what is when something failed, how long did it take to get it, and can you have that part left on site as a spare? Have additional parts as spares on site. So I think there's a way to tackle that from both sides of it.
Definitely. And also, it's not a super common issue where we see these valves failing, but we have had it occur at Climate Pros, and we've actually had to drive parts across the country to get it there within 8 hours because otherwise it would have taken 2, 3 days to get those valves in. So just keep that in mind, help mitigate that downtime, having that spare on site, or like Lou said, having a spare piped in parallel with it can definitely mean less loss of product. So another consideration that can help decrease downtime on your system is also putting in these bypasses around serviceable components. So here we have our liquid dryers on here as an example. There are liquid dryers that it is a common maintenance item, right? So typically we want to make sure that we're changing at a minimum once a year, recommended to do it a little bit more, but it is going to be worked on and serviced on a few times, right? So if we didn't have this bypass in place, we would have to pump the whole rack down, shut the system off, and that means downtime. That means temperatures potentially increasing, right? So with this bypass in place here, as Louis pointed out, we can then open that bypass up, isolate our liquid dryers, and then the technician can remove any of the liquid that's remaining on there and work on changing those liquid dryers out, and your system remains running. So therefore, you have no downtime. All your cases and everything are maintaining temperature, and the technician gets to do his job and change out those dryers to help maintain a clean a system so that you run more efficient, right? So having these bypasses in place can help out quite a bit.
Definitely. All right, and our last one we have is understanding CO2 level. Uh, we got just a minute or two here. When it comes to the CO2 level within your system, something that's a little bit different than the HFC systems is there's more ways to lose refrigerant than just a leak. Right? In the past, if you're at a low receiver level, we're adding refrigerant, that usually means you got a leak, right? We should have been purging it or blowing it to the atmosphere at that point. It would mean that there was a leak in the system. With CO2, there's different ways to lose refrigerant. And I'm just looking from a long-term perspective, if you're doing routine maintenance regularly, you've had a lot of service issues recently, and you got to add refrigerant, technicians should always be doing their due diligence by doing a thorough leak check. But looking at the service log would be just as critical. Did we recently do a service repair where we could have had to release some refrigerant in order to do that repair? So I just like to bring attention to that, as that might be a possibility. Does not get any technician on a leak check, and there should never be a cop out for doing a proper leak check. But it's something that we should always just be aware of. And I think is going to be a little bit different with CO2 than what we've seen in the past.
All right. So in conclusion, guys, you all it is up to you as technicians and employees of the store or managers at the store or even installers to make sure you have the proper PPE and that you're aware of the hazards of CO2. Understanding the system, it can help you know when you have those safety scenarios of what needs to be addressed. All right. We went over quite a bit today, going over what causes trapped liquid and what it means if you have signs of dizziness. So be mindful of that and make sure you're always checking down the line, understanding your flow of refrigerant, checking and knowing where your next shutoff is, and understanding where that refrigerant has to go. that CO2 if it has a place to relief back to the vessel or if it's just an external relief. So, yeah,
Can't
and
stress, yeah, we can't stress enough. Stay safe out there. If something's questionable, call a supervisor, call a service manager. Find, make sure you're doing a job the safest that you can, so that we all go home at the end of the day. So, with that, Em and I want to thank you guys for attending. We've had a lot of fun doing this. It's our first go at it. We had a good time. So we hope you guys did too. We hope you learned something.
thank you guys. I know it's
Thank
been a
you.
hot week. Appreciate you guys all attending.